and welcome to Chapter 9, Vectors. In this section, we're going to talk about something which is a generalization of numbers. So numbers are a way to assign magnitude, right? If you have 3 of something, that's bigger than 2 of something, right? But there isn't really direction to numbers, and you need direction to correspond to stuff that happen, let's say, in real life, right? So if you have a car and the car is going 50 miles an hour, it doesn't tell us in which direction it's going 50 miles an hour. So we might need to specify and say it's going 50 miles an hour in that direction, right? In that direction. And so the way that you would construct a vector to represent it is that that vector would have to point along this direction, right? And then the length of that would correspond to the speed, right? So if you think of velocity, right? Velocity of a car, this has got 2 parts, right? It's got direction, how fast, where you're going, right? Where you're going, and then speed, how fast are you getting there, right? So your velocity, often we confuse velocity and speed, but technically velocity also has direction in addition to speed, okay? So if you think of your compass, right, you have all these different directions, right? The velocity first picks out a direction, and then the length of that vector, that's going to correspond to the speed. So we're going to make all this precise in the coming lectures, but this is just a soft introduction to the material. So now we're going to talk about another way to think about vectors. So another way to think about vectors is that they're collections of numbers. So if you have a vector u and it has, let's say, components 1 and 2, okay? So 1 and 2, this is an algebraic formula, and geometrically it would correspond to position 1, 2, right? Heading in that direction, right? So there's this point 1, 2, right? So here's our x-axis. Here's our y-axis. So in order to come up with the proper vector that corresponds to this 1, 2, you put the tail of your vector at the origin. That's the origin, the spot 0, 0. Okay, 0, 0. That's your origin. And then you draw a arrow with the point at the point where it ends. Okay, so what do we do with these things? Well, like numbers, we can add and subtract and multiply them. And vectors come in essentially 2 forms, column vectors and row vectors. So in this book, we are going to be adopting the column notation. So you're not going to see me write vectors like this anymore. So technically, we should be writing it like this. Okay, 1, 2. Okay. Now, the neat thing about vectors is that the way you put the numbers in the vector matters, right? So 1, 2 is not the same thing as 2, 1. Obviously, they're not written in the same way, but what would 2, 1 correspond to? Well, it would correspond to the vector that looks like that, right? So geometrically it's different, and algebraically it's also different. So this would the length of the vectors is the same. So this would be like saying two cars are going the same speed, but in different directions. Vectors are also useful for solving systems of equations, and this is one very common application in calculus and a field called linear algebra, which is basically vectors and matrices used to solve complicated geometric problems. So let's see, suppose I gave you this system of equations, x minus y, x plus y, z minus 1. And I said that this is equal to 4, 2, 3. So the thing about vectors is they're only equal if each of their components are equal. So when you look at this, you know that z minus 1 has to equal 3 because they're both in the third coordinate, and we said that the vectors are equal to one another. So because the vectors are equal to one another, we have z minus 1 is 3, so z equals 4. For the other two, it's going to be a bit more difficult to solve, but we can write it as a system of equations, and we can solve that. So how do we solve this? Well, there's two methods. So two methods for solving this. Method 1 is elimination. So in elimination, we're going to add these two equations together so that y gets destroyed. So you should have 2x equals 6, right? Because negative y plus y, that's 0y, and then x and x is 2x, and 4 and 2 is 6. So we see that x is equal to 3, and if x is equal to 3, then y has to equal 1, right? So that's 3. Oh, so y has to equal minus 1. Okay, so to summarize, x is 3, y is negative 1, and z is 4. Okay, so that's your example from the book. So what else? How do you add vectors? So some topics we're going to cover. We're going to learn how to add. We're going to add vectors. We're going to multiply vectors with scalars. And we're going to multiply vectors with other vectors. And we're also going to multiply vectors with matrices. Okay, so the first thing we're going to do is work on adding vectors. So this is pretty straightforward. If I have one vector v1, v2, v3, and the subscript, that's just a way for me to call the spot in the vector. And I want to add it to another vector, w1, w2, w3. The way that I do this is I just add the components together. So the new vector is going to consist of v1 plus w1 and v2 plus w2 and v3 and w3. So explicitly, let's go through an example. So 2, 1, 7, and 4, 3, minus 1. So if I add these together, right, I would get 2 plus 4, 1 plus 3, and 7 plus negative 1. And by simplifying, we get 6, 4, and 6. Because when you add a negative number, that's the same thing as subtraction. And that's pretty much it for vector addition. It's pretty straightforward. The one thing you have to keep in mind is that you cannot add vectors that are not the same shape. So for example, if I wanted to add the vector 2, 3 to the vector 4, 7, 8, right? Sometimes people try to add the first two and then they just tack on a 0, something like that. You can't do it, okay? You just can't do it, right? So they have to be the exact same size. So to add vectors, they must be the same size. Okay, so the next thing I'd like to talk about is size of vectors. So at this point, it's going to seem a little odd to talk about size of vectors because they're only a single column, but it'll make sense later why I'm doing this. So let's consider the vector 3, 1, 4. So what's its size? Well, it's 3 rows and 1 column. So that's 3 rows, 1 column. And so strictly speaking, we would say that this is a 3 by 1 matrix. Okay, so matrices are just a generalization of vectors, or another way of thinking of it is that vectors are column or row matrices. So let's do one more vector. So I said that I'm generally not going to do row vectors, but here I'm going to do one real quick. 701. Okay, so this has got 1 row, right, and 3 columns. So this means that it's a 1 by 3 matrix. Okay, so the next thing we need to understand is how to multiply vectors. So there's 2 types of multiplication. There's scalar and then there's vector multiplication. So let's do the simple one first. Scalar multiplication. Okay, so we've talked about vectors, and vectors are objects, mathematical objects that have direction and magnitude. So what about if you only had magnitude? Well, that would just be a normal number, right? But when we want to talk about that in contrast to the vector, we usually just call that a scalar. So a scalar, when you think of scalar, you can think of it as scalar is an ordinary number. So a scalar is an ordinary number. Well, it's an ordinary number specifically in the setting when you're working with vectors. Otherwise, you don't, if you got 2 numbers, say 2 plus 2, you don't normally call those scalars. Those are just integers, Okay, 2 plus 2 equals 4. Right. So how do scalars work? So let's say we have a vector like this, and I give you the scalar 3, and I say multiply this scalar and this vector together. Well, the way that works is you're going to put 3 into each entry, and you're just going to multiply it through. So this is going to give us 24, 3, and 27. It's pretty simple. There are really no other rules for it. Just keep in mind that this is a number and this is a vector. And it does not matter how big your vector is. It just has to be a vector. Okay, so the next type of multiplication is multiplying a row vector and a column vector. So we are occasionally going to work with row vectors, but for the most part, we're going to work with columns. So the next is multiplying pairs of vectors. And specifically, we're going to multiply a column vector and a row vector. That does not look like specifically, but we'll just say it is. Specifically multiply a row and column vector. Okay, so your row vector, right, I'm going to use commas to help separate it. And that's a row vector, and then this is a row vector. Sorry, a column vector. And the way this works is I'm going to multiply together the numbers that I have colored the same way. And then I'm going to add them, right? So multiply the green numbers together, so that's 3 times 7 plus 1 times 1 plus 4 times 4. So this is going to give me 21 plus 1 plus 16. And that's 22 and 16, that's 38. So that's your answer. Okay, so notice that the number of entries in the row was 3, and the number of entries in the column was 3. So they have to match up. If they don't match up, how would you do it, right? So let's say I had 2, 3, and 5, 2, 6, right? How would you do this? You couldn't, right? Maybe you would put 2 times 5 plus 3 times 2, but then what do you do with that 6? There isn't anything you can do with it, at least if we wanted this rule to be consistent, right? So for this reason, the length of the vectors has to be the same. Okay, so that's it for this video. I'll see y'all in the next one.